Okay, so let's get started with today's material, the last material from Chapter 5. Reminder, we have our Chapter 5 test next week. So I'll give you your practice test, and then also bring all your homework from Chapter 5 next week, and I'll insert that into gradebook while you guys do the test. So don't forget those things. Now, we're starting to introduce what we now call methods of integration. Methods of integration. The problem we have with integrals is they are hard. Derivatives are easy. Derivatives are stupid easy. Like if I were to ask you to calculate the derivative of something like x³ plus 1 under the radical, that is a very easy thing to do. Let's just quickly do it. Let's take the derivative of this with respect to x real quick. What do? We bring the 1/2 out in front. Okay, there's a 1/2. And now we view that as to the minus 1/2. Or in other words, a minus 1/2 is a square root in the denominator, square root of x³ plus 1. And then chain rule, we need to multiply by the derivative of the inside, which is 3x squared. Right? Yep. Okay, there we go. That was easy. Now, let's instead try to take the integral of this thing with respect to x.
Take the antiderivative.
Yeah, take the antiderivative of that. Take the integral of that. You figure out this thing, I'll automatically give you an A+ in the class. Why? Because you can't do it. There is no algebraic expression we can write that expresses the antiderivative of that thing.
Why?
Now, there just isn't one. This is not the derivative of some function that you know how to write using exponents, trig functions, hyperbolic functions. There is no function you can write down such that when you take its derivative, it gives you that thing.
Wait, why don't we try, like, can't we just add one exponent and divide by it?
No, because you've also got to get the inside. So try to do it kind of the naive way that you're thinking. Well, shouldn't this just be like x³ plus 1 to the 3/2, right?
Yeah.
And then what else were you thinking? Do we put the 2/3 there?
Yeah.
All right, so let's take the derivative of this and see what we get.
Well, it's not the same.
We take the derivative of that, bring the 3/2 down, that cancels out the 2/3, and we're left with to the 1/2. So we got x³ plus 1 to the 1/2. Okay, great. But then we have our chain rule, times 3x squared. That's not the same thing as that.
Is there a chain rule for...
We got this piece right there, but we couldn't get that right there.
Is there like a chain rule for antiderivatives?
Yeah, that's what we're gonna go over today. We call it u-substitution typically. We're gonna go over the antiderivative version of the chain rule. But there is no way to do this.
Seriously?
Seriously.
Why?
Even with the u-substitution.
Whatever the function is not a function that is expressible in terms of the symbols that we know and love. There is an answer to this thing, but it introduces what we call elliptic functions, which are functions that we can't express with symbols this way, and so we can't get into elliptic functions. It is a very advanced topic relative to what we're doing. And there are types of functions that we just don't have ways of expressing like this. So, derivatives, really, really, really easy. Integrals, really, really, really hard. And even simple things are shockingly difficult. And so if you were to go into your textbook here and flip to the back page, then you would see this thing called a brief table of integrals. And it's going to give you a bunch of formulas for like the forms of integrals we know how to deal with. And it has something like 150. 157 of them. And those are kind of like the way you use your trig identities when you're in trig, often using those to help you do substitutions. There's 157 common forms that we know how to work with, because there's only special forms of integrals that we know how to deal with. And this is not one of those forms.
So generally, there's not an algebraic solution?
Right, there are many algebraic functions whose antiderivatives are not algebraic functions. So taking the derivative, super easy. Taking the antiderivative, extremely difficult. And so we can only work with special ones, and even with our special ones, we've got to learn all the different tricks for the different forms that they could potentially be in. And so we're going to look at one very special form that these integrals can be in, and when we can use a u-substitution. We can basically undo a chain rule. You can view it as undoing a chain rule. So here's one that we're going to look at as our first example. Now notice that this is one that we already know how to compute. It would just be a giant pain. you can multiply it all out,
Yeah.
distribute all the terms, and you have some big polynomial. And taking the integral of a polynomial, that's super easy.
Yeah.
That's one of the forms we love.
Yeah.
So we know how to do this, but who wants to expand out x³ plus x to the 5? That would be a nightmare. How many terms would that have, roughly? 32 if you multiplied it out. 2 to the 5.
Yeah.
Oh, plus we've got to multiply by this. So 2 to the 6. So roughly 64 terms. And then combine like terms and it would reduce to some smaller number. But we don't want to do that.
Yeah.
So here's a form. It's one that we already know how to work with, but we're going to see how a u-substitution, viewing this as somehow asking us to integrate a result of a chain rule, can help us solve it much easier. So what we're looking for is we're looking at this function and we're trying to somehow view it as a function inside of a function where its antiderivative also shows up. Now that was a lot of words, so let me start explicitly writing some stuff out.
Okay.
Let's call this piece right here x³ plus x, let's call that g of x.
Okay.
So we're going to say g of x is equal to x³ plus x. What would g prime of x be then?
3x² plus x to the square,
Plus just 1,
or plus 1,
right?
Yeah.
And now, notice that if we also called f of x just equal to x to the 5, looking at this is now asking me to do the integral of f of g of x times g prime of x,
Yeah.
right? And this looks a lot like the result of our chain rule. When we perform our chain rule. What is the derivative? Let's use a big F here. I'll use big F as the antiderivative of that. So what is a derivative with respect to x of f of g of x equal to?
G.
If we use little f to represent the derivative of big F, it's f, or big F prime.
Yeah.
Maybe, I'm not sure which way will be less confusing to you. F prime of g of x times g prime of x, right?
Right.
Now, if that little f is the same thing as the derivative of this, then that is just f of g of x times g prime of x. And so you see that this is somehow, if we can find the antiderivative of just that little f, then we can somehow view this as the derivative of that big F function. So this is somehow, if we can find the big F here, this is somehow the derivative of that. And so the antiderivative of this thing is just going to be that thing.
Okay.
You with me?
Yeah.
Okay, so here's what we do. We usually let a u represent the inside piece that we're going to be talking about, our g of x. So I'm going to call u this thing right here. So I'm going to say u is equal to x³ plus x. Exactly what we had our g of x equal to. Now, our problem here is we have that dx. If we're going to do a u substitution and rewrite things in terms of u, we need to integrate with respect to u, not with respect to x. So, what is, if u is equal to that, what is du dx equal to?
It's 2x plus
3x
3x squared, sorry. Plus 1 times du dx.
Well, this, if this is u, this is the derivative of u with respect to x. You with me?
Yeah, sorry.
Now, this right here is a symbol. It's the derivative of u with respect to x. It is not a quotient. But we always and forever just treat it like quotients, right?
Yeah.
And we view it as a differential. That way we can move it to the other side and we put the dx over there. And then we say, okay, and we go on our merry way.
Right.
And so now notice that here's my du and here's my u. Now rewriting this function, what is it? It is now the integral of that thing to the power of 5, or u to the power of 5, times, and now notice we did a clever substitution that made all of this just du.
Yeah.
Or in other words, we now wrote it, using our symbols down here, we are now looking at the integral of little f of g of x, which we're now representing with u, with respect to u. So this and this are the same thing. And so, our integral is just going to be, we just need to integrate now f of u with respect to u, which is just going to be big F of u. Because this is the antiderivative of that. So continuing with our example here, I just rewrote all those x's. I say I'm going to write a new symbol that means those symbols. Put u's in there, right? And so we got to here. Now take our integral. What does that equal?
U to the 6 over 6.
U to the 6 over 6. This is our big F of u now. Right there. Now we need plus a constant, of course.
Yeah.
And then finally, we didn't want to know what it was in terms of u, we wanted to know what it was in terms of x. So put your x's back in. And our final answer is that this is equal to, what was u? It was x³ plus x. All to the 6 over 6 plus c. So that would be how we solve that integral.
The whole thing equals that.
Yes, you integrate this and you would have gotten that. Now you could have worked it out by hand and it would have been an algebraic nightmare and see that you got the same thing, but that's what it comes out to.
What if we don't have such a nice example?
What if what?
What if our example isn't so nice? Like we don't have the
Dude, shouldn't have replaced my u.
derivative of u as part of the.
Right, so the whole trick with the u substitution is to somehow view it as a function where we can get the du to replace the dx. We need to find a way of replacing all our x's with u's in such a way that it also enables us to get rid of our dx with the du. That's the whole trick to it. So in this case, our du was equal to 3x² plus 1. Okay, so let's do one more example before we actually do the proof that we can use this u substitution. So
Why do we need to prove it? Isn't that just simple algebraic substitution?
Typically, I wouldn't mind skipping this proof. The only reason I want to go through the proof is to help make it more concrete in your head what exactly we're doing. That's the only reason. It's one that, honestly, I would be fine with skipping, but I think there might be some insight you gain through actually seeing the proof. So let's do one more example, then we'll do the proof, just so you can see it happen in a more generic way. Okay, so our next example, we are going to be looking at the integral. Miss Anandra. Sure. Someone already got me in, but turns out I need one more, so all works out. All right, sec² of 5t plus 1. So we're looking at the integral of sec² of 5t plus 1 times 5 dt. Right?
Yeah.
So here's our problem. And again, you can somehow see that we see like a function inside of a function.
Yeah.
And what is the derivative of this inside function?
5.
Just 5 dt.
Yeah.
Right there. And so we see, I kind of see how this is a derivative of the inside, and it's a function inside of a function. And so this is begging, what is that begging us to make our u?
5 plus 1.
The 5t plus 1, perfect. So we let our u be 5t plus 1. And so what is our du equal to?
5 dt.
5 dt. And so rewriting this using these symbols, that 5 dt we can replace with the du, and that 5t plus 1 we can replace with the u.
Yeah.
And so now this is just the integral of sec² of u du. And what is the integral of sec²?
Tangent is it cotangent?
Just tangent.
Tangent.
So this would just be the tangent of u, but our u was 5t plus 1. So I'm going to skip straight to writing 5t plus 1, and then plus the constant.
Right.
Good?
Can we? Okay. Okay.
All right, so theorem. If we let u equal g of x, then the integral of f of g of x times g prime of x is equal to the integral of f of u. Oh, I forgot my dx there. Sorry. Dx, my integral of f of u du. So again, a really quick proof. that we can do these u substitutions and it gives us the same thing.
Yeah.
With me? So one, start by getting our antiderivative. I'll use big F be any. Remember when we calculate integrals, we could use any antiderivative we wanted.
Yeah.
So I'll let big F be any antiderivative of f. Or in other words, what do I instantly know? I know that the derivative of big F with respect to x is the same thing as little f of x. Right? That's what it means for big F to be an antiderivative of that. I also know that big F, if we were to somehow write it in terms of u, then its derivative would just be little f of u. That's what it means for big F to be the antiderivative.
Yeah.
Okay. So 2. Then, the derivative with respect to x of, oh, sorry. I forgot to also say, let u equal g of x. Let's assume that I said that. We can write it. All right. Let u equal g of x. That's the substitution we want to use. Okay, now we'll come down here. 3. Then, what is the derivative with respect to x of f of g of x equal to? Just using our chain rule.
Just f of g of x.
It's the derivative of the outside times the derivative of the inside.
Yeah.
What is the derivative of big F?
Little f.
Just little f.
Yeah.
So it's just going to be little f of g of x,
Times g prime of x.
g of x times g prime of x.
Yeah.
Is that all I want to write right there? We'll just keep going and see what happens. Okay, so then let's calculate the integral of this thing and see that it gives us the same thing as that. So calculating the integral of this thing. So what is the integral of f of g of x times g prime of x with respect to x equal to?
In terms of u, it's
Well, notice that, well, we're not going to go to u yet. Let's just evaluate this thing. This right here is just that.
Yeah. Right.
So this is the same thing as the integral of the derivative with respect to x
Of big F.
of f of g of x
Is equal
with
to
respect to x, right? And that is equal to, our fundamental theorem of calculus is that integrals and derivatives undo each other.
Yeah.
And so that just gives us
That big F.
f of g of x plus some constant,
Yeah.
which then is just equal to,
why are you adding a constant?
because I took the derivative, when you take an integral, it gives you an antiderivative plus a constant.
I know, but it cancels out with your dx.
No.
No, my g of x is just some function.
Okay.
So this is just the same thing as f of u plus c.
Yeah.
With me?
Yeah.
Now, let's do the other one. What is the integral of little f of u with respect to u?
Oh, f prime, or just f of big F of u?
Just big f of u
Oh, plus constant.
plus a constant. But we already showed that that's what this is equal to. So it's equal to the integral of f of g of x times g prime of x dx. Okay, woohoo, we did it.
Yippee.
Okay, so they give you the same thing. And so you see how this is kind of just undoing a chain rule. That's kind of the way we think about it. So let's do another example now. Lots of examples, I think, do more to help than anything.
Yeah.
So let's find the integral of cosine of 7 theta plus 3 d theta. So this time we're looking for the integral of, I already forgot what I said, cosine of 7 theta, I think it's plus 3. That constant won't really matter, d theta. what is begging to be our u here?
The 7 theta plus 3.
The 7 theta plus 3. But what's the derivative of 7 theta? 7 du. And we only have 1 du. I wish that that somehow had a 7 in front of it. Ah, annoying. What can we do?
Times by 7.
If I multiply it by 7, I also have to divide by 7. And then we're fine. So I'm going to say this is just equal to 1/7 times the integral of the cosine of 7 theta plus 3 times 7 d theta. You see, I multiply 7 there and divide 7 there. Those cancel out. You didn't change anything.
Okay.
Right.
Right?
Yeah.
So that's often going to be the harder part to these problems, giving you a taste for it. The harder part is going to be trying to find some way to re-represent your function as a function in terms of u times du. So we're always trying to make this somehow an f of u du. That's what we're after. And now, that's much nicer. It's exactly what we wished it was. So now, what is our u going to be?
It's going to be 7 theta.
7 theta.
7 theta plus 3. And what is our du going to be?
7.
7.
7 times du.
d theta. Remember, du d theta is equal to 7.
Right, sorry.
So du is equal to 7 d theta.
Right, right.
And again, not the right way to think about this, but the way everyone does is the derivative of u is equal to 7 times the derivative of theta, and you think about it as kind of doing a chain rule.
Yeah.
Not supposed to think about it that way, everyone does. Okay. So now, this is equal to, we can call it the integral of just the cosine of u du. Oh, don't forget our 1/7. 1/7 out front, and then times the integral of the cosine of u times du, right? And now what is that equal to?
Negative sine.
Just negative sine of u.
Yeah.
Don't forget our 1/7 here, so negative 1/7 times the sine of, and remember what our u was. Go back to your initial
Plus 3.
7 theta plus 3. Perfect. All right, pretty easy.
Okay.
Do you times that by 70 theta? Or?
No.
Oh, I forgot my plus 3 here, or my plus c. Now here's an important point. Notice that that 1/7 was time multiplied by this whole antiderivative.
Yeah.
So I need to multiply that 1/7 by my constant, right? Why not? What's 1/7 times a constant?
It's constant.
It's a constant.
Oh.
So let's say that the constant we got from this was c sub 1. Then we'll let c be 1/7 c sub 1. It doesn't change anything.
Gotcha.
So distributing your constant multiplication to your constant, you can do it if you want, but it's just a constant. 1/7 of a constant, just another constant. So it doesn't change anything.
Gotcha.
Okay. Another example. I can't believe I let you guys trick me. No negative.
Is it?
We're not doing the derivative of cosine, we're doing the integral.
Oh.
No negative. Should be checking my answers really quick with the book to make sure I'm not lying to you. What did we get on that one? That was right. What did we get on the first one? That was right. Okay. So that was our only mistake so far. We just did example 4, example 5. x² times sine of x cubed. Okay, so this time we're looking at the integral of x² times the sine of x cubed dx.
So u is x3.
So if we did u is equal to x cubed, what is du equal to?
3x squared.
3x squared
Yeah.
dx.
Right.
Where's this?
Okay, so now, what do we notice? We have an x squared dx, we need a 3x squared dx.
So let's times it by 3 or times by 3.
Yeah, so we're going to do this is equal to 1/3 times the integral. I'll write this piece first. The sine of x cubed times 3x squared dx. You see how everything's accounted for?
Yeah.
That 3 cancels out with that 3. That x² is right there. The dx is right there. The sine of x³ is right there. So we haven't cheated. We just rewrote it to get the integral of some function of u times du. And so now this is equal to the integral of the sine of u times du. Right? Now, I forgot my 1/3. Okay. And now, what is the integral of sine of u?
Negative cosine?
Negative cosine of u. So we got negative 1/3 times the cosine of whatever our u was, x³, plus some constant c. All right. Negative 1/3 cosine x³ plus c. Yay. Next one. Evaluate x times the square root of 2x plus 1. So we got the integral of x times the square root of 2x plus 1 dx. Okay, what do we want our u to be?
2x.
So if we did our u is equal to 2x plus 1, what does our du equal?
So that 1/2 and then plus
X. Dx. Oh, sorry, 2.
2
Dx.
dx.
No, my bad. Yeah.
Right?
Alright.
Yeah.
Now, we're kind of stuck
Why?
because we still have an x there. So I can multiply top and bottom by 2. Let's just rework it to help us see things. So here's what I have so far. I have the integral. We need a 1/2 out front, right?
Yeah.
So 1/2 the integral of x times the square root of u times our other 2 comes up right here. Are you okay with me just writing du? You already see it?
Yeah.
Because we multiplied that by 2 to get du, and we divided by 2 out front. So we haven't cheated. Follow the algebra so far?
Yeah.
Okay, but we still have an x there. I can't integrate with respect to u while I still have an x in there. What are we going to do with that x?
Times by 1/2 x. We do that?
If you times by 1 over x, you also have to divide by 1 over x. You can't just change the expression. To not change the expression, we either have to add 0 or multiply by 1. Those are valid things to do.
Yeah.
But I somehow need to express that x in terms of u. Do I have an equation that could help me express that x in terms of u?
Yes. You.
It's right here. Let's just solve this for x and see what x equals.
That's gonna be u over 2 minus 1.
If u is equal to 2x plus 1,
Yeah.
then minus 1 from both sides. I get u minus 1 is equal to 2x. Divide both sides by 2. And I'm ultimately going to get that x is equal to u minus 1 over 2.
Yeah.
You see that?
Yeah.
Let's make that substitution now and continue on our merry way with this integral. So this is equal to 1/2 times the integral of u minus 1 over 2 times, I'll just write, rather than square root of u, I'll do u to the 1/2 to help us quickly do the algebra. Du. You with me?
Yes.
Okay. Now, let's, I'll skip to down here. I'm going to pull this 1/2 out and multiply by that 1/2, which gives me 1/4, right? 1/4 times the integral of. Now, what is u times u to the 1/2? Let's distribute this through. I need to multiply that to that and multiply that to that. Which u to the 1 times u to the 1/2?
Negative 1/2. U to
What are you doing?
You-
What is x³ times x to the 7 equal to?
x to the 10.
X to the 10. What is x to the 1 times x to the 1/2 equal to?
X to 3 halves.
Oh, I thought it was negative 1.
Oh, no, that's minus 1. So this is u to the 1, and we're going to multiply that, and then we're going to do the negative 1. Multiply to that. We're distributing,
Okay.
right?
Yeah. So it's X to 3 halves.
Okay, yeah. 3/2.
Okay. So this is equal to 1/4 the integral. We have u to the 3/2 minus u to the 1/2. Negative 1 times u to the 1/2 minus u to the 1/2 du. Right?
Yeah.
Okay, now let's evaluate that. Oops, I forgot I came down here. So now that is equal to 1/4 times, what is the integral of u to the 3/2?
To the
5/2
5/2
times 2/5.
times 2/5. That's a 2/5, sorry. Minus, what's the integral of that?
3/2 over
U to the 3/2 times 2/3, right?
Yeah.
Okay, so this is equal to, let's multiply it all out. 1/4 times 2/5
It's 2/20.
is going to be 2/20 or 1/10. 2/20, 1/10, same thing, you see it?
Yep.
So we're going to have 1/10 times u to the 5/2. What was our u? 2x plus 1. So that's this term. Minus, what's 1/4 times 2/3?
1/6.
2/12 or 1/6. So 1/6 times u to the 3/2, and then plus our constant. And so there's our answer, hopefully. What example was that? 1/10 times 2x plus 1 to the 5/2 minus 1/6 times 2x plus 1 to the 3/2 plus c.
Yep. Sweet.
Okay. Let's try another one. Evaluate 2z over the cubed root of z² plus 1. 2z dz all over the cubed root of z² plus 1. I think is what's that.
Okay.
Do we still want to interpret on
We're gonna
Wait.
so we want our u to be z² plus 1.
So we probably want our u to be z² plus 1.
Okay.
So let's try that out. So we'll do u is equal to z² plus 1. What is our du going to equal?
2z.
Finish.
DZ?
dz. Remember, you always got to get rid of your dz and get it into a du. All right, so let's rewrite it this way. This is equal to, we have u to the 1/3
Yeah.
in the denominator is the same thing as u to the minus 1/3.
Right.
Just trying to get it ready for us to integrate it. Right? So that's this piece. Times, this is just du. The whole top part was just du. You
Oh, nice. Sweet.
see it?
Yeah. So
Yeah.
our life is easy.
So our life is easy. So what's the integral?
It's 2/3.
It's u to the 2/3. So u, which is z² plus 1, to the 2/3
Times 3/2.
times 3/2 plus some constant.
Yeah.
3/2 times z² plus 1 to the 2/3 plus c. Okay. All right, two important ones that come up a lot. So the integral of sin² of x dx. How on earth are we going to work with that thing?
Do we know that half derivative is s²?
Do we? That's what we're trying to figure out.
Yeah. You can express that as sine times sine. If you want to.
We can think about sine times sine. Does that get us anywhere? Kind of want to somehow express it as just a single powered
Yeah.
trig function. Thinking way back to your double angle identities.
Fine.
Let's really quick remember what was cosine of 2θ. You remember this one? I'm not sure how far to go back to pick you guys up. This was the same thing as cosine² of θ minus sine² of θ. Do you remember that one, or is that too far back?
I remember it, I just don't remember.
Yeah, I remember that.
You good with this as our starting point?
Yeah.
Because that comes from our double angle. Maybe just really quick, write out our double angle. You might remember this. The cosine of alpha plus beta, this is one that we did our big derivation for, is equal to cosine of alpha times cosine of beta plus sine of alpha times sine of beta.
Yeah.
This is a special case where alpha and beta are both the same thing.
Yeah.
So if it's theta plus theta, then we have cosine theta times cosine theta plus sine of theta times sine of theta. With me?
Yes.
Now I'm going to use this really quick to solve for sine squared of theta.
Why is that minus sine squared of theta instead of plus?
Oh, the other one should be minus, shouldn't it? Shouldn't cosine be negative?
Cosine is
That one.
minus.
Yeah, that's minus.
because I wrote that wrong.
Okay.
So it was plus minus and minus plus here.
Yeah.
Because, yeah, as we make our angle bigger, we make our cosine smaller. Adding beta to it makes it smaller. Okay. So, thank you. So now this equation makes sense, right?
Yes.
Okay, so now we're going to solve for sine squared. But before we do that, I want to rewrite cosine squared in terms of sine squared. Let's put another trig identity up here, the one that we probably use the most, which is that sine squared of theta plus cosine squared of theta is equal to 1. And the Pythagorean theorem on the unit circle.
Yeah.
X squared plus y squared equals r squared, where your r, your radius is just 1. So I'll put the squared there if it helps you see it better. Okay, so I'm going to rewrite this cosine squared in terms of sine squared and then solve for sine squared. So what is that cosine squared equal to? It's 1 minus sine squared.
Right.
And then we minus another sine squared.
Wait.
1 minus. Oh, minus 2 sine squared.
1 minus sine squared is cosine squared.
Just the identity.
R squared minus y squared equals x squared.
Why couldn't we have substituted in our original equation? Why couldn't we have substituted sine squared for cosine squared minus 1?
Because we're looking for what sine squared equals. And notice that I'm going to get sine squared in terms of a single power trig function.
Oh. Okay.
See it?
Yeah.
So doing the algebra here, this is just equal to 1 minus 2 sine squared of theta. Now, let's swap these two sides.
Isn't that plus? There's two negatives there.
No, minus sine squared of theta, and then minus sine squared of theta again. I'm first doing 1 minus sine squared of theta, perform that operation. When you're done, minus sine squared of theta again.
It's 2 sine squared theta. Okay.
Good?
Yeah.
Yeah.
Now this is equal to this. I'm going to move my 2 sine squared theta to this side and move this to the other side. So I get 2 sine squared of theta is equal to 1 minus cosine of 2 theta. With me?
Yeah.
Divide both sides by 2, and I get sine squared of theta is equal to 1 minus cosine of 2 theta over 2. Now for our next one, we're going to be solving cosine squared of theta. We could have done all the exact same algebra. The only difference it makes is it would have been 1 plus cosine of 2 theta over 2.
Yeah.
Why the difference in sign? Because notice that this has a different sign than that.
Yeah.
Okay, so for this substitution, I'm going to rewrite this as the integral of, since we don't know how to work with that, sine squared is the same thing as this. And I'm going to write this as 2 fractions just to make sure we can see it. 1 over 2 minus cosine of 2 theta over 2 d theta. With me? Okay. Now what? Put parentheses like that in case we're getting in trouble.
Did you pull out the 2?
Why is there 2 in the
Make it
denominator there?
1/4?
You pull out the 1/2 already. Why is there 2 there?
No, this is minus.
Oh. I was gonna say.
Oh, okay.
So we know how to take the integral of this thing.
Mm.
What's the integral of 1/2?
It's 1/x.
1/2,
D theta.
1/2 theta, because we're integrating with respect to theta.
Yeah, right. Sorry.
So this is just going to be theta over 2 minus, and we still need to evaluate the integral of this one.
Right. This negative sine
Yeah, it's
of 2 theta. To
The integral of cosine is sine of 2 theta.
Oh.
We have the 1/2 here, but notice that we need to also undo our chain rule. It's like we want u to be 2 theta, so our d theta we need to be 2 d theta.
Oh, okay.
So we want to multiply this by 2 and divide that by 2.
Right.
See if you can follow me all in one step here. If I just go straight to writing, this is the same thing as sine of 2 theta over 4.
Okay.
Notice, take the derivative of this really quick. Derivative of sine is cosine. Chain rule, multiplied by 2, cancels out.
okay.
And then plus c. Oh, he did it with x. So we got the same answer. He just did x's instead of thetas.
How did we get to theta?
Because I just wrote it down that way, going from here to here, because I was looking at those equations.
Oh.
So we would have put a theta there and a theta there, we would have been good. Or replace all the other thetas with x's.
Yeah.
Doesn't matter what we call the variable, right?
Yeah.
Okay, so similar thing now, let's do it for cosine squared. What is the integral of cosine squared of theta? D theta equal to?
Negative sine.
It's just going to be, oh, you're trying to go straight to it? Let's do our substitution. 1/2 plus cosine of 2 theta all over 2. Because this time we're doing this substitution, right?
Right.
And now we want to integrate this with respect to theta. So this is equal to, what's the integral of 1/2 with respect to theta?
1/2 theta.
1/2 theta, or theta over 2, I think is keep it the same. Okay. What's the integral of that?
Negative sine.
Plus, the integral, the antiderivative of cosine is sine,
Yeah.
Oh, yeah. I have
not the derivative. Yep.
Sine.
Sine of 2 theta divided by 4. Because we would have had to times the 2 here and divide 2 there to do our u substitution.
Yep.
And then plus whatever our constant is.
Yeah.
Which,
Good?
Yeah.
All right. That's the end of the first section. The second section is largely about calculating areas between two curves, which we already talked about, and then using u substitutions in definite integrals, not just indefinite integrals. A little bit of whiteboard space in case. So let's just do our first example problem. And we are going to evaluate the integral from 1 to -1. Let's see, 3x squared times the square root of x cubed. So we're doing the integral 3x squared times the square root of x cubed, shoot, was it -1 or +1? X cubed plus 1. From -1 to 1. So now we're calculating this integral. With me?
No.
Now remember that if it was without that piece, no chance of us doing it. Can't be done. Having that piece, now we can do it. Now we're going to be able to do our u substitution.
I see.
So what is our u going to be? What's the u that we want?
X to 3 plus 1.
X cubed plus 1. Sorry, I forgot my dx there. And so what is our du going to be?
2x squared.
3x squared dx.
3x squared dx, which is fantastic. 3x squared dx. So this is going to be the integral of, I'll call it just u to the 1/2. You okay with that?
Yeah.
Times du. Now, we need to make a choice here. We either need to change our bounds, or once we evaluate the integral, switch back from u to x.
Change our bounds to what?
So if x is going from -1 to 1, what is u going from?
Oh.
You with me? So I'm going to do the first one, changing our bounds, and then the next one I do, I won't change the bounds. So you see it both ways. So this might be a change of bound. So as x goes from -1 to 1, because this is iterating over x, u, let's see, when x is -1, what's u? What's -1 cubed?
-1.
Plus 1 is
0.
0. And then plug in 1, what's 1 cubed? 1 plus 1 is 2. So x going from -1 to 1 is the exact same thing as u going from 0 to 2.
Okay.
You with me?
Yeah.
Yeah.
Now evaluate this integral. What's the integral of u to the 1/2?
So u to the 3/2 of 1/2.
U to the 3/2 times 2/3.
2/3, sorry.
Or now evaluated from 0 to 2. Now plugging in 2, what do we get? You have no clue?
I don't know.
What is 2 cubed?
8.
8, and put it under the radical. So we have 2 square roots of 8 over 3.
3. Oh.
That 2's there. This square root of 8 is just u to the 3/2.
Oh.
You could take the 2 and cube it, and then take the square root, or I could have done the square root of 2 multiplied by itself 3 times.
Yeah.
Square root of 2 times the square root of 2 times the square root of 2 is the square root of 8. With me?
Yeah.
Now that's the same thing as 4 times 2. The square root of 4, we can pull a 2 out. So this is 4 square root of 2 over 3. With me?
Yeah.
Okay, let's instead say that we didn't change our bounds. So let's pretend we didn't change the bounds, and so we got to here. We needed to now rewrite it in terms of x. So now this is going to be 2/3 times x³ plus 1 to the 3/2, evaluated from -1 to 1.
That's it.
Yeah. If we're doing these bounds for x, or we can change our bounds for u.
Yeah.
And so, when we plug in 1, what do we get? 1 cubed plus 1 is 2. 2 to the 3/2 is square root of 8 times 2/3. So we get 2 square roots of 8 over 3, which is the same thing as, oh, but now we need to minus what we get when we plug in -1.
Right.
When we plug in -1, we get 0.
Oh, yeah.
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 It has to end up plugging in 2 and plugging in 0, because that's what we got when we changed our bounds. It's just a matter of when you do that algebra. It doesn't change anything. So then we would get minus 0, which once again is equal to 4 square root of 2 over 3. So either do the algebra early and change your bounds, or do the algebra when you go to plug in. Those are your choices.
Okay.
It's not saving you work one way or the other. You're going to have to do all the algebra. 4 square root of 2 over 3, right? Okay. Just make sure we didn't mess anything up. Okay. This next one, for pi-4 to pi-halves of cotangent of theta times secant squared of theta. So we're doing the integral of cotangent of theta times secant squared of theta, d theta. And this was from, I think, pi-4 to pi-halves. Okay?
Okay.
All right. What is our u going to be here?
That's a good question. Secant squared.
What's the derivative of secant squared? No, what's the derivative of tangent?
Secant.
And I wrote this wrong. Duh. This is times cosecant squared of theta, which makes a lot more sense since we're associating it with cotangent. Okay, now what should our u be? That's a lot easier to see.
Secant.
What's the derivative of cosecant?
What is the tangent?
It's
Secant.
negative cotangent times cosecant. You could do that.
Yeah.
Or we could let u be cotangent. What's the derivative of cotangent? Cosecant squared, negative.
Yeah. Either way,
You guys have got to get comfortable with your trig,
Yeah.
taking derivatives of your trig, you need to be able to just recall that off the top of your head. So if we let u be, doesn't matter which of those we choose, I'll just do cotangent of theta. Then our du is going to be negative cosecant squared of theta. Theta, good. And so we just have u du. And so this is equal to the integral of u times du. Doesn't get much easier than that.
Is it u times du because there's a negative cosecant?
Oh, thank you. Negative sign in front. Good catch. All right. Everything look right? Now, do we want to change our bounds now or later?
No.
Let's just do it now. Okay. So as cotangent goes from pi fourths to pi halves, what does u go from? So when we plug in pi fourths for cotangent, what comes out? We're looking at cosine over sine, but we're looking at the reciprocal of the slope. What's the slope at pi fourths?
1.
1. What's the reciprocal of 1?
1.
Okay. That was easy. Need to get my button. Next, plug in pi halves. What's the slope at pi halves?
0 over 1. Or,
Oh, wait, what?
yeah,
It's undefined because it's 1 over 0.
Yeah.
What's the reciprocal of that?
0.
0 over 1, which is 0.
Wait, we can do that?
Yeah, you can do that.
Well, it's just, cotangent is just a reciprocal of tangent. When you try to evaluate the tangent at pi halves,
Oh.
you get 1 over 0. So cotangent is 0 over 1.
Right.
Okay, so there we go. We're just evaluating this integral from 1 to 0. So this is going to be equal to, going from 1 to 0, that's begging for me to make a mistake and accidentally do my 1 minus my 0. So I may have flipped my bounds and make it negative.
Yeah.
Always a good idea if you're worried you're going to make an algebraic mistake.
Well, it works out anyways because it's with a negative.
Right.
Yeah.
So it's nice, it cleans it up, and typically a good idea if you're worried you're going to make an algebraic mistake. Okay, now let's evaluate this. What's the integral of u?
U squared over 2.
U squared over 2. Plug in 1,
You get 1.
1/2, right?
Yeah.
Now minus what you get when you plug in 0.
Which is 0. 0.
And so the answer comes out 1/2.
Okay.
Yeah, kind of shocking. If we were to look at the area of this function from pi fourths to pi halves, the area underneath the curve would be 1/2. A little bit surprising.
A little bit.
Okay, let's try another example. I did that. X to the 4 minus 4x² plus 6. X to the 4 minus 4x² plus 6 with respect to x. And our bounds are from -2 to 2. Okay, before we evaluate this function, a nice thing to note about even and odd functions. Remember what an even function is?
Yeah. It's the same. It produces the same output as the negative.
Right, so a function is even if f of x is always equal to f of negative x. So pick some point, 2 and -2 have the same height. 1 and -1 have the same height.
Yeah.
And so what's the geometric interpretation of that? What does the graph look like?
Parabola.
Well, not necessarily a parabola,
It's symmetrical.
but it's symmetric with respect to the y
Yeah.
axis.
Okay.
So whatever it is, it could be some function. Let me write some random even function. I'll try. I think you'll understand what I'm trying to do. Trying to make it somewhat symmetric. Then if we do the area from -a over here to a, notice that that's just going to be double the area going from 0 to a.
Yeah.
Yeah.
So if your function is even, then the integral of f of x with respect to x from -a to a, as long as you're going, starting and ending at the same point but positive and negative, then this is equal to the same thing as just 2 times the integral from 0 to a of f of x dx. Why is that useful information? Because when we evaluate our integral, we love plugging in 0.
Right.
It's a nice thing to plug in.
Yeah.
You with me?
Yeah.
Now, an odd function, the definition of an odd function is f of negative x is equal to negative f of x. So the height at the left-hand point is the negative of the height at the right-hand point. What does that mean? Let's draw some odd function. What's the interpretation of that?
It's
Like a cubic.
Yeah, cubic is a good example of an odd function.
symmetric across the origin, right?
It's symmetric with respect to the origin,
Yeah.
but that means whatever area you have over here is perfectly canceled out by area over here. So now if our function is odd, if I know that my function is odd, then the integral from negative a to a of f of x is always equal to 0.
Oh, okay.
Because they're just going to perfectly cancel it out. So when it's even, it perfectly doubles it. When it's odd, it perfectly cancels it out.
Yeah.
You with me? Okay, so now looking at this function, what do we notice right out the door?
It's even.
It's even. All those are to an even power.
Yeah.
Plugging x into this and negative x into this gives you the same thing. Right? Because it's always squaring it. Or to the 4 or to the 6. It's always an even number, so plugging in a negative number, it will always come out positive for what you plug in. Okay. So this then is going to be equal to what? Rather than going from negative 2 to 2, what can our bounds be?
0 to 2.
Right, we'll just do 2 times the integral from 0 to 2 of whatever this thing is. Am I making sense? Right?
Yep.
And now let's evaluate that integral. That's going to be 2 times
X to the 5
x to the 5 over 5
minus
Minus
x 2x squared
2x squared.
plus 6x.
He was doing 4x squared over 2, cancel 2's out top and bottom, leaves you just 2.
Yeah.
Okay, and then plus 6x.
plus c at least.
Plus c.
Not plus c because we're evaluating, it's a definite integral. So
Oh.
we're evaluating this from 0 to 2. Now we just need to plug in the 2 and then double it because plugging in the 0 comes out 0.
Right.
Okay, so what is 2 to the 5?
32.
32. Should we distribute this 2 through as we go?
Sure.
Or is that too much?
We can do that.
We can do that? Okay. So 32 times the 2 is 64 fifths
Yeah.
minus
8.
4 times 2 is 8 times 2 is
16.
16. You okay if I write 16 in terms of fifths?
Sure. Yeah.
What is
80 fifths
this?
plus
24.
24.
oh, maybe we should have left that different and then calculated fifths after we do this subtraction here. So this was 8, and then we'll do plus 24.
Which is 32.
Did we do everything correctly?
I think so.
I sure hope so.
Yeah, we did.
Yeah. I think so.
Okay. Oh wait, that wasn't an 8, that was a 16.
Or.
Okay, right?
Oh.
4 times 2 is 8 times 2 is 16. Did we do this one right? 12 times 2 is 24.
Yeah.
Yeah.
Okay, so I got negative 16 plus 24 is
8.
8. In terms of fifths, what is that?
40.
40 fifths plus 64 fifths is
104 fifths.
104 fifths.
It's not kills me,
They got 232 fifteenths.
What?
Going from here to here, I missed my square.
Oh.
Which is going to change everything, right?
Oops.
Oh my goodness.
Silly.
That would probably be fine. Okay. Continuing on our merry way.
Minus
So that was minus 4x³ over 3,
Yeah.
right? And then plus 6x still. Okay, now we're evaluating this from 0 to 2. And we're going to get 64/5, same as we had before. Minus, for this one, what are we going to get? 8
32.
times 2 is 16,
Yeah.
times 4 is
64.
64.
Thirds.
Thirds, plus, that should still just be 24, right? Because we didn't mess up that term.
So now you put everything in terms of 15, so you combine them.
What is 24 times 15?
Is there not going to be,
They have can't do it, right?
all right, yep, so let's start dealing with this.
Times that by 3.
Yep, so 64 times 3, what is that?
It's 192.
Right? Minus 64 times 5, what's that going to be?
320.
320.
Oh, that's 15s, by the way, not 5ths.
15s, thank you.
And then
15.
360.
Plus 360 over 15. Okay, now
That turns into 40 15s.
we got the 40 plus the 192, right?
Yeah.
So what's that going to give us?
232 15s.
232.
Is that what I got?
I don't remember. 232 15s. Okay, yay, we did right. All right.
And there's no way to say that.
Now, next one, we are supposed to find the area in the region enclosed by the parabola y equals 2 minus x squared. So we're looking at y equals 2 minus x squared, and y equals negative x.
Okay.
So we're looking for the area in the region enclosed by those curves. For these problems, you are going to need to draw a picture the majority of the time. So let's try and get a picture for what this looks like. Now, first off, I want to know where these two curves intersect each other because we're looking for the area